All right. So today's materials will be completely sufficient for your second assignment. However, next week also will be helpful. We will do some extra materials. So you will be much more professional about your second assignment. However, as I said, today's will be enough. So first question tells us that have a look at the Taylor's theorem and then apply the third order Taylor's series or Taylor's theorem. For third order, it means in the 3 plus 1 or the fourth one will be your remainder or local truncation. So it is y prime equal f. It is the standard way that which is given to us. So what was the Taylor's theorem in the first lecture of this week? Yx equal to be ya. A is the initial point. Here is a equals 0. And y prime a, x minus a, y double dash, plus so on until m. Derivative order m. So that's why we call this one Taylor's series order m. And the m plus 1 is in the role of remainder. And the sign will be between the initial point and the target point x. So if I assign x by x plus h and assuming that a to be equal x, then x minus a will be just h. And the Taylor order 3 becomes like this. Y of x plus h, y of x, h times y prime x, this guy until 4. So this is the order 3. The last term is related to the local truncation. Okay. So we can, by Taylor's series, we are able to discover many things. Discover different numerical methods for solving Euler's. However, you know that from Math 1120 and 2310, yx and h times y prime x, this is like this is the Euler's method. You have seen the Newton's method for solving ODEs, for solving the approximation in Math 1120 or 1110. Okay, everything is like relying on the Taylor's series or Maclaurin's series. Now, this question asks us that y of 0 is given. Have a look, calculate y of 1/10 by using the third order Taylor. Okay, so y of 1/10, y of 0, this guy, this guy, this guy. The fourth one, we will assume that this is tending to the 0. All right. So y of 0 is 2, y prime of 0 is this guy. So I just obtained it from the question. So y prime of 0, this one. So I'm able to calculate y double dash by taking derivative of this one in terms of just x. Y or derivative of y in the order 3 comes from the previous derivative, second order. So which I have written here, y prime of 0. So to calculate y double dash of 0, y order 3 of 0 is, so we have this one, y double dash. Okay, so we can sub this one. So from this guy, we can calculate third order of the derivative, so which is this one. So respectively, we can obtain y order 3 of 0. Okay, therefore, so what is the task? The task is just you see, okay, just substituting. So this numerical things, it's not good if you do it by your hands. Okay. You will do lots of heavier calculations. The theory is easy. So if so other place in universities, conferences, if I say I used Euler's method, I shouldn't say that actually, because it's nothing. Okay, it's not fancy to say I used Euler method. No. But if you can say that, yeah, I implemented Euler's method in, for example, Julia, Python, SageMath, it is, yes, it can be something. So the Euler's method, first y of 1/10 is this one. So the remainder one is the local truncation. Not global, local truncation. In every step, we have this error, this amount of mistake. So I tried to obtain this guy, like I wrote something to hope that we can obtain something, but I couldn't. So I just stopped there, but I didn't erase as well. All right. Now, y of 2/10 is relying on the previous step. Y of 1/10, this guy is up to here is in Euler's method until here. So then you can just substitute and obtain y of 2/10. All right. So nothing. Question 2. Y prime of this guy, the standard way. So y of x. So this analytic solution is given to us. The local truncation, which one will be this one? The local truncation for the Euler's method is O h squared. What is big O notation? We're just playing with the notations. It's just, in other words, we can say that local truncation, local error is something times h squared. But global truncation is, it is possible to prove that it is something times h, not h squared. So local truncation always will be less than global truncation, which is obvious. Now, y double dash. So what's the part A? Part A tells me that find the local truncation. Local truncation is this guy. So h squared is obvious, 2 factorial. So we so y double dash of c. Where c does live? In every local truncation, it lives in the previous point and in the new, between this point and this point. Old and new points of x. So what is y double dash? Y double dash comes from taking derivative from this guy. You can take this this one, but it is meaningless to obtain from this one. So you can obtain it from this one by taking derivative from the right hand side. One derivative will be enough. So you see what I have done here. So 2 minus this guy. So but y prime is already itself is this guy. So what I do is just substituting, simplifying. Okay. What is y? So I just used again I actually so no y 9y minus 6c minus 1. So for y I just used this guy. Yeah, but if it was not given, it was hard to obtain. So I should leave this guy here. So okay, this we've got this one. Where does C lives? C lives between 1 and 1.1 plus H. But we can get the until 1.5. So we can say the C lives between 1 and 1.5. So local truncation, anyway, it's like this guy here. So easy. So, but in part B, it says that this guy here, see 1.5. So here you see that C here, C is between 1 and 1.1. If I assume this H 1.1/10, okay? So C is here, or C is here, but anyway, totally union of them is this. C belongs to 1 and the end point 1.5. Now, local truncation if H is this guy and y of this guy. So C is here, H squared over 2y double dash C. The general formula for that is this guy. And exponential, this guy here, I just stopped here. Exponential e to the minus something is decreasing function in terms of that argument. So we will choose, if I want to obtain upper bound, I will choose the minimum of this argument, okay, which it means C equal 1, C equal 1. So the minimum, if I want to obtain this guy, I would choose C to be equal 1.5, but we want to obtain the upper bound, so it means C equal 1. So if I sub here, it will be 1900s. Any question? All right. Now, part C. Part C tells me that Euler's method, this guy, with H equal 1/10 and H equal 500ths. So it is obvious what I did here. All right, you see this guy. It is, I shouldn't explain the Euler's method, what I did here. Y of 1.2 is relying on the previous one. We will do the rest of the job in the SageMath. Part D, important. Now, the analytic solution, from the analytic solution, which is given to us, it is 1.5. Y of this point is this guy. So analytic solution is this one, is this guy. I just sub x by 1.5. So I obtained y of 1.5 from this. Yeah, so exact point is this one. So what is the global truncation if I use H equal 1/10? It is y of exact minus Euler method with this step is this guy. So the absolute value of the difference of them is this guy. Now, let's make step size twice finer, twice smaller. So instead of 1/10, I use 500ths. So y of step size minus y of 500ths with H subset of 500ths. At this point, 1.5, it will be something. So their absolute value will be this one. But it's not important. So we will see in the SageMath. Now, let's have a look at the explanation. We know that the global truncation of the Euler's method is something times H. Big O notation of H. Okay? So it means something times H. If H gets finer twice, Okay, the global error will be gets again the global error will be like twice smaller, twice finer. So because it's linear relation, C times H or big O notation H. So it means the global notation, global error, 1/10, okay. So this was like 0.2 something. The global error with the finer H was 0.1 something, okay. If I divide them, so I will get 2.1 in the real ones. But actually we expected already because H1, H2 is big or notation of this guy, and this is something times H1, something times H2, almost cancelable, and this will be H1 divided by H2. It means this one, if it is twice, it will be 2. Okay, so let's go to this part. All right. Now, you see this one here, question 2. Question 2 is given to me. All right. Is this recording? Yes. Okay. Just a minute. Yes, it works. All right. So this one. Okay. Question 2. Let's have a look at that again. What's the time? We should be faster. Okay. So you see this one here. We've got this question, the analytic solution, it's given to us, although we didn't need it, we were able to obtain it. Okay, so let's implement so one by one, I will explain. So, this is we're gonna use Euler's method, question part 2, part C, and D. What happened to the question 3? Yeah, so it is easy, you will have a look at in the tutorial solution by yourself. Like, this is the right hand side, which is compatible with this one. Yeah. X, Y, so it is the variables of a polynomial. So this is the way that we can define X, Y are variable. In MATLAB, we say that symbolic or sims, X, Y. Now, PTS is the list here. Okay. X is just the initial value and Y is the 5, which is just compatible with this one. Variable, this PT will be a vector pair. This is a variable. This is another way to define variables. This is a pair including XYs. And we will these XYs to a list of the points that I can show it just points. What is points? Points is a list of the list of the vectors. So list of the vectors is called in Python tuples. Okay, list of the vectors. It is not list. List is just set of the numbers. So I in the range of this guy. Let's assume that what is the X? X is the X is this one, 1. Okay, what is the B? Target, 1.5. So what is the difference? 0.5. What is H? 0.1. It is 0.5 divided by 0.1, it is just 5. So the range can be only this, or between 1 and 5 plus 1. Okay? Intentionally I have written like this. Other places I will just write this guy. So because I want to confuse. Now, K1, sometimes we have K2, sometimes we have K3, K4, where in the higher orders. K1, in Euler's method, we have just K1. Improved version, we have K1 and K2. In Runge-Kutta, we've got until K6. So I just apply the, get the first term and second term. I update my point. After obtaining this, I assign them as a 1-point vector, and I assign this vector to the list, which is called PTS. So this PTS, it has PTS1, PTS2. The first one is regarding to the first elements, which is X, X's, and Y's. So I've got this guy, so I can apply this. I can get this 0.1. See this guy here. So the way that we define function, it's given in my YouTube. Okay. You can implement this method in every language. Okay, but the way of defining variables might be different. All right, so we can obtain this this final version as well. This guy. All right. What are the final answers? Y is here, and Y of this here. Part D. So let's calculate the error. Let's do this, the last one. Error analysis. Analytic solution is given to us. I just copied from the top here. So analytic solution, it is easy to write this in SageMath. Just this one equal this one. If you wanted to define this one in Python, okay, you cannot write in just one line. One line is not enough. So this one function easily defined. So I just sum 1.5. So I obtain the precise value of y of 1.5. Now, so let's do the error analysis here properly. Page 110. First error, what is that? The absolute value of analytic solution minus, where did I get this 1.807 from here? See here. Now, I've got this one as well. All right. So the difference of them is this guy, 0.23, this one. The difference of this one, and with final step, y of 500 at the point of the 1.5 is this guy. Okay, so the ratio will be 2. Ratio is this guy. Yeah. Now we want to practice SageMath like more. Number 1. The analytic solution. We didn't need that one because we are able to obtain with using this DE solve. Okay, DE solve, no arguments, no auxiliary package. So it is this guy, and if you simplify it, which I couldn't do that in SageMath, but if you simplify by hand, you will get the same answer. Now, let's do this question 1. Question 1, you see that it is this one, y prime of this guy. Again, also, what I did here is just nothing. I'm not smart because what I did is just copy from there and paste it here and just I changed this one. Can you do that? Yes, of course. All right. So this guy here, I changed this guy. I was careful about my initial points. This guy, and Euler. Okay. So y of 1/10 in question 1, y of 0 is given to us. y of 0 is 2.
You have initial points as arguments.
In the D is all yes. D is all yes. We look at this one, 1, 5.
Yeah.
This guy. So that's why we don't have K1, K2, C1, C2. Okay. Now, Euler's method via 110 with the step size is 1 divided by 10,000. Okay. Can I? You don't want to see this, of course. Yeah, the last, this guy is this one. All right. So the solution I obtained from the tutorial, like PDF. It is this guy. Okay, you want this. Solution here is with the step up 1/10. Step up 1/10, and in one shot, I just wrote this. Step size h equal with order 4. Okay. Local truncation is h14. Since we did one step, the local truncation and global truncation is the same. Okay, so it is this guy. What is the local truncation of the Euler's method? Is this guy. Something times h. Okay, so if I want to get the same answer, I want to get this solution here Euler divided by solution of the this guy from the I copied just from the PDF. I wanted this guy to be 1. This means the same precision. Okay, this is the 1. Why I have chosen 1 over 10,000? Because global truncation is h14, but it should be h123. But since we did one step, we are happy with power 4. This guy is h2. Okay. Now, to get 1, you see that these guys should be the same. This guy is this one, but h1 is 1 over 10. This means h2 should be 1 over 10 power 4. It means 1 divided by 10,000. So order 4, order 1. See the difference. Okay, so if we are lazy, we can use Euler's method. If we are not, we can go to the higher orders. Improved Euler is okay as well. Runge-Kutta is very famous, and most of the PhD students in engineering, they use this, and in mathematics as well. Now, but it's the matter of the speed as well. Okay, so the speed of your compilation is also important for you. Maybe you've got 10,000 small differential equation ODE, and you want to do you want to solve 1,000 of them or 1 million of them in C++. In C++, it is hard to write this implementation, so you are happy with the Euler's method. You write it and you test it, it works, so you run it for a few days and it works. But if you have less equation, you're happy with, you can do like higher orders. Now, let's do other example. Y prime of this guy. So, all right, this is IVP. Now, what do we do that? Let's write this like not complicated version of the Euler's method. See, I just didn't do anything. Over there it was like my arguments like step size and target number. Here I've got initial value of x, initial value of y, step size, target of the x, target x. So what is this? Integer x target minus x initial value divided by h. Simple loop. Okay. And I get just, okay, if I have this one, y of 0, y of target, y of 5/10, step size 1/10. this is 0, this 0 here, and 1 there as well. Now, so I see this guy. So I'm happy with this. Now, what is, so if I apply x step size 2/10, I will get this. All right. So let's measure the time that we need for this. Import time, and so there is the same thing in MATLAB as well. You can measure the time of the claim that your algorithm is faster. So importing the module time. In Python we say module, not package. This time module, and this time should, this guy A, this should be between these for starting and ending times, printing this the result and printing the time as well. So this guy. So very small number. Okay, 10 power minus 5. All right. So we can use Euler's method, simple Euler's method, in the SageMath. Yeah. But we didn't use it, but we want to use this one. So Euler's method is given to you. So the command is this. But in the assignment, you are not allowed to use the inhibited commands. Although I think there is not for Hume's method in there in the SageMath. It's not established. It's not ready. You need to prepare it by yourself. So if I Euler's method, it has this output. Okay. If I measure the time of the same thing in the step size 1/10, the same target, I will get this time. The time will be this one. The result is the 0.37. Okay, see, the result is 0.37. Okay, but the time is slower. Your algorithm, our algorithm is faster than this. If I apply the previous algorithm, okay, the time is still better than the SageMath inhibited command. Okay, it means if we develop our own algorithms, if you implement this algorithm, your work will be faster than whatever is inhibited in the SageMath. All right. So you can test other things here. Okay. What else we can do? So what are those? This X, Y, as I said, is the way of the defining the variables. So if you don't write X, Y, it will give this output. Your name is two variables. This means X, Y is the variable of a polynomial of coefficient.
Hi, sorry to interrupt. Did you have this room booked? Because we've got this room booked from 9 to 12. So
yeah, we will finish at 9.
You finish at 9.
Yes.
Okay, thanks.
Yeah. So X, Y. All right. If you make a small mistake, you will have this nice message. Okay. Yeah. So if you put this algorithm equal to be none, it will be X, Y. So you won't have extra stuff. Okay. This is better because you're able to plot your results. Okay. So same thing. This is another question. 2xy. First Euler method. Y of 1 is 1. Its step size is 2/10, and the target is 1.6. Here is step size 1/10, finer, smaller. If you are able to plot this. See, the blue is the finer one, the red one is the lazy one. Now, DE solve, you can use the DE solve this guy here. Okay, then you can plot square of this stuff. Multiply by 2 and square of everything here. Okay, so you will have this. You can solve this DE solve. You can use this DE solve by Euler's method and then DE solve together, and you can see that as you the step size is finer, you will be closer to the exact solution. So you see the other examples here. You see the vector field, how to do that in this one. Vector field with the small exact solution and the Euler's method. Sometimes it's not working, but Euler's method is working. Exact solution, the SageMath was unable to solve this initial condition analytically, but it is able to solve it by Euler's method. Yeah, so anyway, at the end of the file, I have put an improved Euler algorithm, K1 and K2. Please have a look at that, study that. If you change this one slightly, you will get the Hume's method. And be careful that don't use the Hume's method from the Wikipedia because it's different. Whatever, you should use the Hume's method just using the context of this course. Good luck.